Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to use the idea of equivalent resistance to simplify a circuit down. So what we're looking at right here is a relatively simple circuit. So imagine we've got this 12 volt DC voltage source here attached to a circuit that looks something like this. We've got this 6 ohm resistor here. Circuit comes down to this point, splits off. Here's a 10 ohm resistor, 5 ohm resistor. And what we're going to do here is we're going to try to find all the currents in the circuit. And most circuit problems basically boil down to finding the currents, because whether you're interested in the currents or maybe the voltage across a resistor, that would be calculated by current times the voltage, or maybe you're interested in the power output of the circuit, finding the current usually is required for most any circuit questions. Now, before we even move on with the problem, it's important to recognize how many currents there are in any given problem. So you have to identify how many different branches there are. I'm going to go ahead and use some colors here to show this. So here's a branch basically that starts here all the way around to there. Right? There's one branch in the circuit. There's going to be a certain current in that branch. You're going to get the same value whether you put an ammeter here, here, or here, anywhere in that circuit. And whatever the value of that current is, I'm going to give it a name, and I'm just going to call it I1. I'm going to go ahead and draw it in my picture. Oops. So the current in this branch right here, I'm going to put in this direction, gave it a name I1. And again, it's very important to recognize that that current is good anywhere in this branch to that point. Right? Now, at this point, the current gets kind of divvied up. There's a junction there. Some of the current could go up through this part of the circuit, some of it this part. So we have two more currents, and I'm going to just call them I2 and I3. So I'm going to call the current through the 10 ohm resistor here. Use a little arrow. Oops. Go ahead and do that in black. I'm going to go ahead and put an arrow for the current direction, give that a name. I'm going to call that I2. And we're going to have and let me back up. I2 is good in this branch. Right? Then we have another current going through this part of the circuit, so I'm going to go ahead and put an arrow here, darn it, in the same color. Put an arrow in this part of the circuit, call that I3. And again, important to realize I3 is good anywhere in this branch. All right, now there's a couple different ways to analyze the circuit. One way is to just start writing loop equations for the circuit. We could write 3 equations, solve for the 3 unknowns, and I think what I'll do is just use another video here to do that. And here what I'm going to do is the idea of equivalent resistance. So the idea is to somehow simplify the circuit down into something that's less complex. So here we have a pair of resistors, and this is a parallel combination. So what I'm going to do here is I'm going to calculate the equivalent resistance of that combination in parallel. All right, so I know that 1 over R equivalent is equal to 1 over 10 ohms plus 1 over 5 ohms. And this is coming from how resistors in parallel are calculated. If you haven't, at this point, if that's completely foreign, if you back up, I've got a video where I talk about how equivalent resistances are calculated. I would review that. If I go ahead and solve that for R equivalent, and I'm not going to worry about putting the math on the video here, I get 3.33 ohms. So what that means is that this combination here in parallel is equivalent to a single resistor with a value of 3.33 ohms. Now what I'm going to do is redraw the circuit. So this circuit now is going to be equivalent to this, right? Got my 12 ohm voltage source. We've got our 6 ohm resistor. And in place of these two, we're going to put a single resistor with a value of 3.33 ohms. Right. Now, the current I1 in this picture, basically, I'll just put it basically right in the same spot. There's I1. And that current is good anywhere within this loop. Go ahead and put the plus minus signs on the plates. All right, now at this point right here, we could just write an equation. We could write a loop equation. You know, starting here, that equation would be plus 12 minus 6I1 minus 6i, minus 3.3i3 equals 0, solve for I1. I'm going to go ahead and just continue on with the idea of equivalent resistance. This pair of resistors, the 6 and the 3.3, these are in series. So to calculate their equivalent, our equivalent is going to equal 6 ohms plus 3.33 ohms, and we get 9.33 ohms out of that. So I'm going to go ahead and redraw the circuit with a single resistor with a value of 9.33 ohms. And although it may seem like a lot of work, you do want to redraw the circuit. Every time you find an equivalent resistance, redraw the circuit. So basically what we found is that this 9.33 ohm resistor is equivalent to this combination of resistors in the original problem. And again, getting to back to this, you should put all the currents, relevant currents, in each picture. So we found the equivalent resistance of the system. Now what I'm going to do here is start get rid of this. Start working the problem. I don't need this anymore, so I'm going to just get rid of it. Okay. So, how do we use equivalent resistance to solve the circuit problem? Well, looking right here now, whether we use Ohm's law, which is V equals IR, or we write a loop equation, I'm going to go ahead and write a loop equation. So imagine starting right here, I'm going to go ahead and go around clockwise and write a loop. So, you know, I always imagine like a little bug walking across the circuit. As I walk, the little ladybug walks, and when that ladybug goes over this battery, it's going to increase in potential, because we're going from minus to plus by an amount 12 volts. Probably should have labeled that earlier. So we're going to have 12 volts. Now my ladybug keeps walking. When the ladybug crosses this resistor right here, that's going to be a drop in potential by an amount IR. So it's I1, and the R is 9.33 ohms. Right, now our ladybug is back to where they started, so equals 0. No, we don't need this. All right, if we solve this for I1, I'm going to take a moment here and see what I get. Boom, 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 boom. I get about 1.29 amps. Okay. Now that we have I1, right, from this picture, that I1 is going to be true everywhere. So it's going to be good in this picture, and it's going to be good in this picture. There are a couple different ways to solve this problem. What we could do, because we know I1, we could figure the voltage across here now. Here's one way we could solve this problem. You see there's a 12 volt potential here. This 6 volts, this 6 ohm resistor is going to have a drop in potential by an amount I1 times 6, which we could calculate. By the time we take 12, subtract off the voltage drop across that resistor, we would then know the voltage here and here. We could then calculate the current here. Then we could move back to this original picture and use this current. Let me back up on that. Once we know the voltage here, if I move directly to this picture right here, that's going to be the voltage between here and here. Then we could apply Ohm's law to get this current, Ohm's law to get this current. So I want to just talk about, you know, one kind of conceptual way we could work this problem. This is how I would work it. When, you know, this is a relatively simple example. I try to keep my examples in the video to the simpler ones, because the purposes of the video are how to apply these concepts. And sometime down the road I'll work a more complex example and put it on the video. But I like to use methods that work all the time. And usually when you're working a fairly complex circuit problem, a real good way to handle it is, you know, use the idea of equivalent resistance to find a current. I usually go back and just start writing loop equations now in the original picture. And this is a very robust method. Now that I1 is a known value, we can write a series of equations for the original picture here that will only have one unknown. So I'm going to go ahead and do that. So I'm going to do this loop right here. And that loop will only contain one unknown, I2. So I'm going to go ahead and write the equation for that loop starting right here. And what we're going to have is plus 12 volts when we go across the battery. Then we're going to have minus the current through this resistor we already found to be 1.2 amps times the resistance, 6 ohms, All right, so that's going to get us good to this point. As I come down here, no difference in potential, no difference in potential, no difference in potential. Here, when we go across this resistor, we are going to drop in potential by an amount. All right, so voltage across resistor is IR, so we're going to drop by an amount I2R, which is times 10 ohms. And then we're back to where we started, so equals 0. If we go ahead and solve this for I2, I've already done that. I'm just going to write down my results. Solve that equation for I2, and I get 0.43 amps. Right. Now there's a couple of ways we can go through getting I3. Any equation we write that has this resistor in it will get us I3. I'm going to go ahead and write an equation for this loop right here. I'm going to starting here. Right. I'm going to be doing that loop now. Now I know that that's not necessarily the shortest equation we can write. Again, I'm doing this for demonstration purposes of how to write these loop equations. So again, starting here where I said, moving across here, we're going to have plus 12 volts. Right, and now when we go across here, there's going to be a drop in potential by an amount I1. Whoops, I guess I'll go ahead and just put in the number. 1.29 amps times 6 ohms, right? Drop in potential because again we're going with the current. All right, so as I move along here, looking at the circuit, when we move across this resistor, we are going to drop in potential by an amount I3 times 5 ohms. All right, and then looking at the circuit, we're back to where we started, so equals 0. If we solve this for I3, I get 0.85 amps. And we basically now know all of the currents in the circuit. So we basically know everything there is to know about this problem. Quick little check here. People always ask me, how do I know if we're right? Well, you know, there's several things we can do with circuit problems to check it. I guess I'm going to check this. Notice right here at this junction, right there, the current I1 is coming into that junction. The currents I2 and I3 are going out. I'm just going to check by the conservation of charge law, basically coming into that junction. Whatever comes into that junction has to go out. You'll notice that coming into that junction is I1, which we found to be 1.29 amps. Going out is I2 and I3, 0.43 and 0.85. If you add these two together, you can get 1.28 out of that. So it differs, you know, to the third significant figure there, and that's just rounding. You know, I usually work these in two significant figures. So for all practical purposes, they do add to current I1. Some other things about this circuit I'd like to point out, you know, how to answer the questions. Now that we have the currents, any questions about potential, like potential difference across maybe this 10 ohm resistor right there, we could calculate by I2 times 10 ohms. Same thing with the other two resistors. Any power questions, you know, we could calculate the power here by I2 squared R. We could calculate the power here by I3 squared times R. Here we would use a 5 ohm resistor. And we can calculate the power here, and we would have I1 squared times 6 ohms. Now, if we added those three numbers up, we would get the total power output of the circuit. We should be able to come here and take I1 squared times 9.33 ohms and get the same value. So I think I'm just going to end this video right here. This was just intended to be a short, fairly easy example to follow on how to use equivalent resistance to simplify a circuit down. And I hope that this video demonstrated that for you. Have a great day.